Our next session is on the topic Unraveling Neural Networks, Foundations and Insights, led by Dr. Shailesh Sivan. For the introduction, I once again invite Ms. Prasida E., Assistant Professor, Department of Computer Science and Applications, St. Mary's College, Autonomous, Thrissur, to introduce the speaker. Ma'am, please take over.
Thank you, Ms. Guido. Once again, good evening, everyone. I am delighted to introduce our esteemed resource person for our next session, Unraveling Neural Networks, Foundations and Insights, Dr. Shailesh Sivan. Dr. Shailesh Sivan is a Principal AI Architect at Laennec AI All India Private Limited with rich experience spanning over both industry and academia. He has also served as an assistant professor in the Department of Computer Science at Cochin University of Science and Technology, CUSAT. His areas of expertise include deep learning, machine learning, computer vision, natural language processing, data science, and quantum computing. He has an impressive record of publications in reputed international journals and conferences. He has authored several book chapters and a textbook aligned with the KTU Dept curriculum. Dr. Shailesh is also a patent holder, having developed AI-powered innovations and has delivered more than 150 invited talks and workshops in India and abroad. He is an active member of professional bodies such as IEEE, ACM, and CSI, contributing significantly to the AI community. We are truly privileged to have him with us today, and I am sure his insights will enrich our understanding of neural networks. Let us welcome Dr. Shailesh Sivan. Sir, please.
Yeah, thank you, ma'am. Yeah. We can start with a very new topic and a very interesting topic, particularly in the field of artificial intelligence. This is a breakthrough, and what all magic we are experiencing nowadays with AI, that is the ChatGPT, the LLMs, Gemini, all is actually founded from this point. Okay, and this can be considered as the foundation for all these innovations that we are experiencing nowadays. So, particularly, this topic is very much close to my heart. Like whenever I am taking this particular topic, I'm feeling very happy that people are getting more interested in this particular topic, and it is a very beautiful topic too to understand, and it will give you the essence of how the AI is actually working in a human-like fashion. Okay, so let's start with a classification task. You're all familiar with these terms, right? Classification, clustering, regression. Can anyone tell me what is classification? What do you mean by classification? Anybody please unmute.
They're segmenting the data into different classes.
Okay. We have to segment the data, or we have to map the data into multiple classes, right? And how can I formally or mathematically define classification? See, like the data I will be having is X comma Y, and this is called as the labeled data, right? We will be having the data as features as well as the labels. Okay, and within this X we are having each data point, which is described using n features, and this Y is a particular categorical value. Then only it is called as a classification task, right? So in classification, what we have to do is we need to find, okay, we need to find a relationship. We need to find a relationship that connects this X and Y, or we can say that we have to find a mapping phi that maps from the set X to Y. Okay, that maps from X to y. And after getting this mapping, on applying a new x, where x is an element of capital X, you will be getting some kind of predictions y cap. And the objective of this phi, we have to find a phi in such a way that the difference between, that is, we have to find a phi where the difference between the actual label and the predicted label should be minimum. We have to find such a phi. And finding such phi is actually called as a classification algorithm. How to find such a phi. Okay, that is what we are explaining in a classification algorithm. So according to different theories, we can actually find such kind of mapping phi in different ways. Okay. Sometime it can be a probabilistic values. Sometime it will be a tree information theory based trees. Sometime it can be a mathematical equation. Sometime it is a decision rule. So based on different theoretical aspects, we will find different algorithms to find such a mapping from input x to output y. Okay, hope it is clear. So we are just revisiting a classification problem. Okay, and I'm not giving any name for this. Okay, I'm not giving any name for this. This is not KNN, this is not NA base, this is not HVM. So this is some generic classification algorithm G. Okay, and how I can explain this generic algorithm? See, suppose we are having a data like this, X, and the features, only one feature is there. It's a univariate data, only one feature. And this feature is actually mapped to a particular label. And how many labels are there? Only two labels are there, right? So this is particularly called as a binary classification. Can anyone tell me why it is called as a binary classification? I know you are all knowing this, but to make it engaging, I'm just asking. You know why it is called as binary classification?
Because of two classes.
Yeah, the mapping is happening to two classes, right? So it's a univariate binary classification problem. Okay, univariate binary classification problem. Right, fine. So here what is happening is some general feature x is there, and that x can have values -2, 6, 7, 3, 2, -1, 0, 5, like that. Okay, and each of these values associated with a particular label, either positive or negative, right? Now suppose I have a new value called -7.3. What will be the label for this? Is it N or is it P? By seeing only this table, will you be able to tell me what it is? Is it positive or negative? What do you think? It is difficult, right? It is difficult to say that. So what we are doing is, we are simply visualizing this data as it is a univariate data. We can represent that data on a simple number line, right? So I'm representing -2 here. See, this is -2, this is -2. And since it is negative, I'm representing it as a red circle. 6 is there. 6 is again representing it as a green circle. Likewise, on representing our data on this number line, you are able to find a pattern here, right? What is the pattern you can observe? All the red data points, right? All the red data points are clustered in a particular region of the number line, and all the green data points are clustered in another region of the number line, right? So that is a pattern. And to represent that pattern, or to to make a decision based on that pattern, I'm considering a particular threshold value. Okay, the threshold value can be any value between this 4 and 5. But for not being biased, I'm simply taking the midpoint as the threshold value. That is theta equal to 4.5. Right? And what is the rule here? All x values less than 4.5 is mapped to red, and all x greater than 4.5 is mapped to green, right? So this is our rule. And to represent this rule in a very particular way, see what I'm doing is, my decision boundary is x is equal to what? 4.5, which is nothing but x is equal to what? 9 by 2, right? That implies 2x equal to 9, or 2x minus 9 equal to 0. So I can represent my decision boundary in the form of a linear equation of the form ax plus b. And what is the peculiarity of data? What is the peculiarity of all points here at this region? If you put these values, okay, these values in this linear equation, it will satisfy the inequality 2x minus 9 less than 0. Otherwise, it will be satisfying 2x plus minus 9 greater than 0, right? So, on getting this threshold, or on getting this decision boundary, I can make a decision rule here. What is that rule? If there is a new point P, and if you substitute on this equation 2x plus minus 9, okay, that is 2p plus minus 9, and if you are getting a value less than 0, then that particular p will be mapped to negative class. Otherwise, the p will be mapped to positive class, right? So can you just apply this point here? If you take minus 0.5, what will be the value? 2 into minus 0.5 plus minus 9. That is minus 1 minus 10 minus 10. And it is less than 0, right? So minus 0.5 will be mapped to what? Negative. And if you consider some value here, that is 8.5. Okay, 8.5. What will happen? 2 into 8.5. 2 into 8.5 minus 9, which is equal to 17 minus 9, which is equal to 8, which is greater than 0. Then this point will be mapped to the positive value. Is that clear for you, everyone? Please, can you just respond on the chat box? Is it clear with this concept? Yes. Okay. So, after understanding this, if you are clearly understanding this particular thing, you can think about the next version of this problem. That is, see, if you're moving from a univariate data to bivariate data, moving from univariate data to bivariate data, that is, we are having two features here, x1 and x2 as features, and there will be a label y, right? So our data is described using two features, right? Right? Our data is described using two features. So how can I represent? We can recall the concept in the previous class. There, the two features will be represented as a plane, which is nothing but the r square, right? Which is nothing but the r square. So every data point will be a point on this plane. Okay. Every data point is a point on the plane. And some of them are positive and some of them are negative, right? Some of them are negative. Okay. Now, how can you distinguish between these two classes? In the previous case, as it is a number line, we will be able to find a point that represents or that separates two classes, right? But here, as we are having a two-dimensional plane, how can I do this? In what way we can do this? What is the possibility? Instead of a plane, instead of a point, we have to consider what? We have to consider a line that separates two classes, right? We have to consider a line that separates two classes. Okay, so this line is having a general representation ax plus by plus c equal to 0, right? Now, what is the peculiarity of all points at this region? This region is represented by the inequality ax plus by plus c less than 0. So whatever point at this region is substituting on this equation, you will get a negative value. Otherwise, you will be getting a positive value, right? So with this, you can make a decision rule. How can you make a decision rule? See, on getting a new point PQ, and on getting a new point PQ, if you substitute P in the place of X and Q in the place of Y, then it becomes AP plus BQ plus C. And if you are getting a negative value for this inequality, for this particular equation, then it will be a negative class observation. Otherwise, it will be a positive class observation. Hope it is clear, right? Okay. And similarly, you can extend this particular concept into three-dimensional data. Three-dimensional data means we are having three features, x1, x2, and x3, and the label is y, right? So there, the data will be represented in a three-dimensional space instead of a 2D plane, right? So here, the data will be scattered over a space, 3D space, right? And here, to separate these two classes, okay, what we need to separate these two classes, can we do it with a line? No, right? Instead, we need a plane that separates two classes. Okay, plane that separates two classes. Okay, so that plane is represented as ax plus by plus cz plus d equal to 0. Right? Ax plus by plus cz plus d is equal to 0. And again, the decision rule is PQR. Right? That is the new point. And substitute that on this equation, that a into p plus b into q plus c into r plus d. If it is less than 0, that it will be negative. Otherwise, it will be positive. Right? So, hope it is clear for you, right? Now, just think about the decision boundaries I have taken. In the first case, it is simply ax plus b equal to 0. In the two-dimensional data, it is ax plus by plus c equal to 0. And in the third case, it is ax plus by plus cz plus d equal to 0. So can you relate what is happening here, the decision boundary? If you have one feature, the decision boundary will be a linear equation with one variable and a constant, and that variable will be multiplied with a coefficient. If you have two features, x1 and x2, the decision boundary is represented using a second degree linear equation, right? Each variable is multiplied with a coefficient, and a constant term will be there. And if you are extending that to three-dimensional data, okay, three features, it becomes a third degree linear equation, that is ax plus by plus cz plus d equal to 0, right? Three variables, three coefficients, and a constant. So if you think in that way, in this way, can you extend this idea into n-dimensional space? What will happen? What will happen in the n-dimensional space? That is, if one of your data is represented using n features, one of your data will be represented using n features, our data will be a point on an n-dimensional space, right? Now, what will be the decision boundary? What will be the representation of decision boundary? As I said, this decision boundary will be an nth degree linear equation, right? N degree linear equation. And that n degree linear equation is represented as n variables x1, x2, x3, etc. up to xn, each multiplied with a coefficient w1, w2, w3, etc. up to wn, and a constant of theta. For the simplicity, I can represent this as sigma wi xi plus theta. Okay, right? And also I can represent this in a vector form as, see, the product of w1, w2, etc. up to wn1, sorry, theta, into x1, x2, etc. up to xn comma 1, right? And this vector is w, this vector is x. So I can represent this as vector w dot x. Okay, that is another representation. I can also represent it as a column vector w, which consists of w1, w2, etc. up to wn theta, and x is equal to x1 1, right? So what will happen to multiply this? I need to take the transpose of this, right? W transpose x. What is W transpose x? It will be the column vector w1, w2, etc. up to wn theta into x1, x2, etc. up to xn1. So w1 into x1 plus w2 into x2, etc. up to w1 into xn. So this representation is also equivalent to W transpose x, right? And what is this representation? What is this representation? What is this? What is this equation, or what is this n degree linear equation represents? It represents nothing but what? Any idea? Anyone? Can anyone tell me what is it? It is called as hyperplane. Okay. This is the n-dimensional hyperplane, right? So an n-dimensional hyperplane is represented using any of this equation. See, it can be represented as sigma wi xi plus theta equal to 0, or it can also be represented as w dot x equal to 0, or as matrix representation w transpose x is equal to 0. Is it clear? And the decision rule is nothing but, see, if there is a new point p1, p2, p3, etc. up to pn, and you have to substitute this p1, p2, p3, etc. up to pn on this equation. And if you're getting a negative value, it will be a negative data point. Otherwise, it will be a positive data point. Okay, is it clear? If you understood this, half of the things are clear. Can you just put a response on the chat box? Okay, fine. Now we can move to the core aspect, that is neural network. You may be worrying that why I have explained all those steps, right? You can now connect it, right? So neural networks are special kind of machine learning algorithms which relies upon the human nervous system, or how the human brain is actually getting work. Okay, so we know the human nervous system is represented, or the neuron, a simple neuron is represented like this. Dendrites is there, nucleus is there, a cell body is there, axons. We receive inputs through dendrites, we process the inputs at nucleus, and we pass the results through axons, right? Similarly, in artificial neural network, we are actually modeling a neuron as a perceptron. Okay, as a perceptron. So a perceptron is having a structure like this. It can receive n inputs like dendrites, x1, x2, etc. up to xn. Okay, and these inputs are actually getting multiplied with a particular set of values called weights, w1, w2, etc. up to wn, right? And what is happening at this part, at the nucleus? Nothing but the product obtained from each input, that is w1 into x1 plus W2 into X2 plus W3 into X3, etc. up to W1 into Xn will get added together at this point, right? So that is what we are representing as sigma I equal to 1 to n Wi Xi, right? And if this product is greater than a threshold value, then we map the output as 1. If it is less than 0 theta, we map it as y equal to 0. That is what we have described here. Okay. So you can relate it, right? And if you simply rearrange this inequality by taking theta to the left side, what will be the rule then? Y equal to 1 if sigma I equal to 1 to n Wixi minus theta greater than or equal to 0. Otherwise, that is y equal to 0 if sigma I equal to 1 to n Wixi minus theta less than 0. Right? Now, can you tell me what is this representation? What is this representation? Do you remember what we have discussed at the end of that classification technique? This is nothing but a hyperplane. Okay, this is nothing but a hyperplane. So ultimately, a perceptron is mathematically represented as what? A hyperplane. Okay, a perceptron is mathematically represented as a hyperplane, right? So finding a perceptron for a particular problem, finding out a perceptron for a particular problem. Finding out a perceptron means finding the values of W1, W2, etc. up to Wn for a perceptron is simply finding a hyperplane with the parameters W1, W2, etc. up to Wn. Is that clear? Now the question is, for a given problem, for a given data set, how can you find this hyperplane or how can you find this perceptron? Okay, so that is what we are explaining in perceptron learning algorithm. Okay, perceptron learning algorithm. So we have to recall the concept we have discussed in the previous class. See, suppose I said for every representation, okay, W dot X or W transpose X, whatever it is, if this is a hyperplane, okay, if this is a hyperplane represented using this equation, W transpose X, the vector W will always perpendicular to it. Okay, the vector W is always perpendicular to it. Okay, we know what it is, right? Okay, now see how we have devised this perceptron learning algorithm. Okay, what is the purpose of perceptron learning algorithm? What is the purpose of perceptron learning algorithm? If there is a binary classification problem, what is the purpose of a perceptron learning algorithm? Please, someone unmute and tell me, please.
Sir, to fine-tune the coefficients of the parameters.
Okay, that is, we have to find a hyperplane, right? And for finding that hyperplane, we need to adjust the values of weights or the coefficients, right? So, say, suppose I have some data here, okay? These are some data. See, suppose we are having some data, okay? These are some data, okay? And these are negative data points, and I'm taking some positive data points also here. Okay. So what will be the property of an ideal hyperplane? How should be the ideal hyperplane? If you consider the ideal hyperplane should be properly separating the classes, right? So these are all what? Right hyperplanes. All these things are right hyperplanes because all the data is separated using this hyperplanes, right? But at the beginning of the process, there is no constraint that it will properly separate these two classes. Okay, it will properly separate these two classes. Okay, so what we are doing is, at the beginning, we will randomly find a hyperplane. Okay, we will randomly find a hyperplane. But unfortunately, see, this hyperplane is not proper. This hyperplane is not proper. And as I said, the hyperplane is represented as W transpose X. And what is this X? Each of this point can be X. Clear? Hope it is clear for you, right? Okay. Now, according to this hyperplane, this green data point should come at this region and this red data point should come at this region, right? So these two are misclassifications. Okay, these two are based on the hyperplane. I could say these two are misclassification. Okay, these two are misclassification. See, this is one misclassification and this is another misclassification, right? You know it, right? And after doing the training process, you have to get rid of this misclassification and the hyperplane should properly separate these two classes. So what can I do for this? So if I have a misclassification like this, okay, this is X, right? And as I said, this is our W. This is always our W, right? Okay. So if this is X, I can consider a vector which is particularly opposite to this as minus X, right? Okay. Now, what is the resultant vector? The vector addition, the triangular rule. This will be what? W minus X, right? So if you update this W as W minus X to make it perpendicular to the new W, the hyperplane should also change, right? If this is the new W, to make it perpendicular to hyperplane, the hyperplane should also change, right? So on this updation, what will happen? The misclassified data now become properly classified because the data become a valid data becoming the valid region. Here also the green point come above the hyperplane, right? Is it clear? So what we have done is, if there is a misclassification, a negative misclassification, we will update our weight by subtracting the current input from it, Wt minus X. If there is a positive misclassification, okay, we can update our Wt as Wt plus X. On doing this thing multiple times for every data point which is misclassified, finally you can arrive at a proper set of W's which will give a hyperplane that properly classes all positive points and all negative points. This technique is exactly described in perceptron learning algorithm. You can see this. See, in perceptron learning algorithm, we have a set of positive inputs and set of negative inputs, right? P and N. Okay, a set of positive inputs and negative inputs. Okay, and we will randomly initialize W. What does that mean? We are considering a random hyperplane from it. Okay, and until we converge. What do you mean by until we converge? All the positive should be represented as positive and all the negative should be classified as negative. Until we converge, we have to randomly pick one input from either P or N, that is represented as P union N. Then if it is a positive point and w dot x is less than 0, that's a misclassification, right? This is the way to find the misclassification. If the point is actually positive and on multiplying with w, if it is giving a negative value, that is a positive misclassification. So in the case of positive misclassification, you have to update w as w plus x. And in the case of negative misclassification, that is x belongs to n and w dot x greater than 0, you have to update w as w minus x. On doing this repeatedly until we converge, we will arrive at a proper set of w's which represents or which classify the positive points as positive and the negative points as negative. Hope the idea is clear for you, right? Okay, now we can have an example for this. After that, you will be having a more clear picture of this. Okay, so in general, a perceptron is actually having n inputs, x1, x2, etc. up to xn, and w1, w2, etc. up to wn. And to accommodate that theta, the threshold, we will be having a constant input -1, and this theta is considered as another weight. Okay, and this is called as a bias. Okay, and together this, we will be getting a hyperplane in the form of sigma wi xi minus theta equal to 0, right? And this output from this point will be passed to another function phi, which is called as activation function. Okay, I will explain you what is activation function. And from the activation function, you will get the exact output. Okay, so why we need to have this theta? Why can't we keep the hyperplane as wixi equal to 0? Wixi equal to 0. What is the need of keeping this theta? What is the need of keeping this bias? Is there any particular reason for that? Anyone?
There may be some bias in choosing the parameters. There may be several parameters that may be influencing the model, but we are choosing a limited number of parameters in order to avoid complexity. So that may be.
Yeah, I can explain that in another way. See, I will show you one particular example. This is Desmos I have shown you yesterday. See, suppose we are having a data, okay, like 0, 1, sorry, 1, 0, 1 point, and -1, 0 is another point. Okay, right? Or I can put it as 1, 1 and -1, 1. And another class, the negative, the positive class, it is 1, -1, 2. Okay, and the next is 2, 1, 2. Okay, so these are the two classes. Okay, you can see the positive classes and the negative classes. Okay, and this is a second degree data, right? Or a two-dimensional data, right? So what is the equation of a hyperplane if theta is not there? It will be in the form of ax plus by equal to 0, right? So if you put this, you can change any value for a and b, but the thing is, you will not be able to find a line or a proper value for a and b that makes this line separate the two classes properly. Why? Why we are having that constraint? Because this line is represented as ax plus by equal to 0, right? So what is one trivial solution for this equation? 0, 0. That makes the constraint that the line should always, or the hyperplane should always pass through the sender. If such a constraint exists, then what will happen? Some kind of data distribution cannot find a hyperplane that separates the classes properly, right? And how can I tackle this issue? I can simply add one more term, theta, okay, that is C. And if you have such a C, see, by adjusting the C also, what will happen? You will be able to tackle that problem. Are you getting this? Right? Hope you are getting the idea of why that theta is important, right? By introducing that bias term, you will get more freedom to move your hyperplane away from the origin. So that will help you to tackle more problems in a very easier manner, right? Is that clear? Right. Okay. So, so this is the full architecture of a perceptron model. You will be having inputs, you will be having weights, the bias term, the activation function, and the output. Right. Now we can have an example of AND gate. You are all familiar with the AND gate, right? AND gate is nothing but it can be considered as a bivariate binary classification problem. Bivariate means we are having only two inputs, and why it is called as a binary classification? The output labels are either 0 or 1. Okay, so what is the actual model we can design for this particular problem? We need to have two inputs, x1 and x2, corresponding to A and B, right? And the bias term -1 and theta, and the output is y, that is 0, 0, 0, 1. Okay, so this is our perceptron. So how can I arrive at the proper set of weights? By following the algorithm. Okay, this is the decision boundary, right? Z is equal to w1 x1 plus w2 x2 minus theta. This is the decision boundary. So according to the algorithm, we have to consider a random values for w1, w2, and theta, right? So we have taken w1 as 1, w2 as 1, and theta as 2.5, right? And our data is distributed like this. You can see the points 0, 0, 1, 0, and 0, 1 is labeled as what? 0, negative observations. So here it is 0, 0, 0, 0, 0, 0, 1, and 1, 0. And 1, 1 is represented as positive point. That is on the purple color. Okay. And initially, the hyperplane is not properly distinguishing our two set of data, right? If it is an ideal hyperplane, it should come like this, but this is not the ideal hyperplane. Okay, why? Because we have randomly choose this weights, right? So how can I arrive at this weight? By following the algorithm. Randomly pick one input. Okay, the current weights are 1, 1, and minus 2.5. Randomly take the input, that is one random input, 0, 1. It is a negative data point. And on substituting this 0, 1 on this equation, 1 into 0 plus 1 into 1 minus 2.5, it is a negative value. So we have taken a negative observation, we got a negative value, right? And in the second iteration, we are picking the input 1, 1. And obviously we know this is a positive input. But unfortunately, on applying this 1, 1 on this hyperplane equation, 1 into 1 plus 1 into 1 minus 2.5 is minus 0.5, right? So it is a positive input, but it gives a negative value. So that is a misclassification, right? So if there is a negative misclassification, what we will do? We have to add, sorry, it's a positive misclassification. So what we have to do? We have to add the current input. What is the current input? 1, 1 to the current weights, 1, 1. So the new weights will be updated as 2, 2 minus 2.5. Now we are taking the next input 0, 0. It is a negative data point. And on applying 0, 0 on this new weights, you will be getting minus 2.5. This is clear. And the next input is 1, 0. That is also a negative input. You are applying that 1, 0 on the new hyperplane. That is 1, 2 into 1 plus 2 into 0 minus 2.5. That is also negative. So it is fine. So we have explored all the data And finally, what is the hyperplane equation we have? 2x1 plus 2x2 minus 2.5 equal to 0. So on representing that, you can see the new hyperplane is moved from this to this, right? So this at this stage, you can see this hyperplane is having all negative points at the one region and all positive points on the other region. Okay, is that clear? Everyone, is that clear? After finding this hyperplane, we are applying this inputs in this equation, in this hyperplane equation. So 0, 0 is giving minus 2.5, 0, 1 is giving minus 0.5, 1, 0 is giving minus 0.5, and 1, 1 is giving 1.5, right? So what would be happening here? The outputs from the perceptron is minus 2.5, minus 0.5, minus 0.5, and 1.5. And we have to get the output, or we are expecting the output as what? 0, 0, 0, 1. Okay, 0, 0, 0, 1. So to do this transformation, we will apply the output from the perceptron to another function, which is called as unit step function. It is defined as f of x is equal to 0 if x less than 0, otherwise 1, right? So all these negative values will be suppressed to 0, and all this positive value will be mapped to 1. And this is what we are calling as the activation function. Okay, activation function. Hope it is clear, right? So on experimenting with another gates, see, AND gate is fine because the data distribution is like this and you are able to find a hyperplane, right? And in the case of OR gate also, the data distribution represent, or for 0, 0, it is negative. For 1, 0, for 1, 1, and 0, 1, it is positive. So this is also can be separated using a hyperplane. But what about this XOR problem? Is that XOR data linearly separable? Is that XOR problem linearly separable? Is it possible to find a particular line that separates
No,
these
sir.
two classes? No. That is one of the major block happened in the domain of artificial intelligence. Okay, one of the major limitations. After this problem encountered, there was an age called dark age of AI, or AI winter begins, because people were thinking like such a simple problem like XOR cannot even be solved with artificial intelligence or neural network. Then how can we use these things for bigger problems? So what happened is people actually stopped doing research on it. People stopped working on it. The fundings were freezed. No advancement were happened. So after for a long period, there was nothing happened in the domain of artificial intelligence. Then someone came up with a new innovation based on a theorem called universal approximation theorem. Okay, based on a new theorem called universal approximation theorem. That is, they have designed a network of perceptrons. They have designed a network of perceptron which can actually work, or which can actually depict any real valued function. Okay, it can work according to any continuous real valued function. And how it is happening? That network of perceptrons designed to tackle this non-linearity is actually called as multi-layer perceptron. Okay, multi-layer perceptron. So in multi-layer perceptron, what happened is the input nodes, the input are mapped to multiple neurons, multiple perceptrons, and the output from the perceptrons, first layer of perceptrons, are given as an input to the next layer of perceptron. Likewise, it is actually designed in a feed-forward manner. Feed-forward manner. What do you mean by feed-forward manner? The output from one layer of neurons are actually given as an input to the next immediate layer of neurons. Okay. So such architecture is actually called as multi-layer perceptron. So on getting this alignment, you can see The first set of input layers are there, and the final output layer is there. And in between, there are a set of layers that are represented by several neurons, right? That layers are actually called as hidden layers. Okay, those are called as hidden layers. So what is the significance of this? So with this hidden layer, we can actually handle the non-linearity and how this is getting happen. Okay, so in most of the neural network classes, uh, the faculty members will skip up this concept. They will simply say by moving from perceptron to multi-layer perceptron, you can actually handle non-linearity. Then you can solve XOR problem. But as curious as a student, I always wanted to know how this particular structure is handling the non-linearity. Okay. So do anyone have any idea like how it is happening? Even though if we are knowing that, it is very difficult to convey that to the students, right? Most of the time. So this is a particular way I have designed or my own way of explanations to explain this concept. For that, what I have done is, see, we have the XOR data, right? We have the XOR data, and particularly this XOR data is not linearly separable. Okay, but if you simply eliminate or simply ignore one data point, if you simply ignore this one data point, what is the data point? This data point, the rest of the data is this one, and this one. So at this case, is it linearly separable or not? If you simply ignore one data point, is it now linearly separable or not? What do you think? The negative data point and the positive data point. Is it linearly separable or not? I'm not getting any response from you. Yes, it is linearly separable, right? So definitely you are able to find a perceptron for that. Okay, you're able to find a perceptron there. But what is the peculiarity of this perceptron? This perceptron O1 will give correct input for 0, 1, 1, 0, and 1, 1, but it will give a wrong output for 0, 0. That is fine. Okay, wrong output for 0, 0. Okay, so O1 is capable of tackling all other inputs other than 0, 0. Right. And in the second case, what I'm doing is I'm simply ignoring the last input, that is 1, 1, and 0. Now the data points are negative points and the positive points. Sorry, the negative point and the positive points. Okay, is it now linearly separable? Yes. So you are able to find a perceptron here too, right? O2. But what is the peculiarity of O2? O2 will give an incorrect output for 1, 1. For all other cases, you will get the correct output, right? Now, consider this O1 and O2 simultaneously. Okay. So if you give the same input on O1 and O2, for 0, 0, O1 will give a wrong output 1 and O2 will give a correct output 0. And for both 0, 1 and 1, 0, O1 and O2 will give the correct outputs, right? And for 0, 1, so for 1, 1, O1 will give the correct output, O2 will give the wrong output, right? So what are the possible outputs from O1 and O2? It can be either 1, 0. It can be either 1, 0. How I could get 1, 0? If I give the input, 0, 0, O1 will give the output 1 and O2 will give the output 0, right? And I could get 1, 1 in the case of both 0, 1 and 1, 0. And I will also get another combination, that is 0, 1 for the input, 1, 1, right? Right. So the possible inputs towards this Z is 1 0, 1 1, and 0 1. In the case of 1 0, the actual output we are expecting is 0, right? For the 1 0, the actual output is expecting is 0. For 0 1, for 0 1, the actual output we are expecting is 0. For 1 1, that is the case of 0 1 and 1 0, we expect the output as 1. Okay. Now, can you just think about this particular data? For 1 1, it is positive. For 0 1 and 1 0, it is negative. Is it possible to find a perceptron for this problem? Is it possible? Yes, right? So that perceptron is actually Z. That will work according to this table, right? Now, can you imagine what is the output from Z if you give inputs at X and Y? On giving X and Y as 0 0, on giving X and Y as 0 0, O1 will give the output 1, O2 will give the output 0. On 1 0, the Z will give the output what? 0, right? And this is correct now, right? And for 0 1, O1 will give 1, O2 will give 1, Z will give also 1. So this is correct. And for 1 0 also, O1 will give 1, O2 will give 1, and Z will give 1. This is correct. And for 1 1, O1 will give output 0, and O2 will give output 1, and 0 1, Z will give the output 0. That is also correctly predicted, right? Okay. So together this O1 and O2 and Z, we are able to handle what? XOR problem. Okay. That is how the non-linearity is handled in multi-layer perceptron. So here, this is the input layer, this is the output layer, and this is called as the hidden layer. Right? Hope it is clear for you, right? Okay. So the intuition of this hidden layer is that whenever you increase the number of hidden layers within a multi-layer perceptron network, what will happen? That network can handle more complex decision boundaries. Okay, more complex decision boundaries. So the next question that will come in your mind is, suppose you're having a network like this. Okay, suppose you're having a network like this. There will be 3 inputs. Okay, there will be edges that connect to different neurons, right? Okay, how can you find this weights? How can you find this weights? Okay, what are the possible ways to find this weights? The weights are not actually found, as I said in the example. That is only a simple explanation to understand multi-layer perceptron will solve a non-linearity. But the story behind how to find that weights is entirely different. The only one thing I want to convey from that example is, with a particular set of structure and a set of weights, you can able to handle what? Non-linearity need, right? And see how this is happening. That particular way of finding that weights within the multi-layer perceptron is actually accelerated with a particular technique called the gradient descent method. As I said, what is gradient descent? A gradient descent method is nothing but, see, suppose you are having a function, a multivariate function, we will start at a random point. Okay, we will start at a random point. Okay, and from that random point, we have to reach this minimum point, optimum point. And how can I reach? What is the systematic way to reach that? It is nothing but, on the starting point, you will be having some kind of gradient, right? So you have to move in the negative direction of gradient to reach the optimum point. That is what we are calling as gradient descent algorithm. Okay, gradient descent algorithm. So from one point, you have to move towards another point. And what is the strategy for that? We have to move towards the negative direction of the gradient. Okay, so theta j, see, I can show you an example. See, this is one function. Okay, this is one function. You will be starting at this point. Okay, this is x0. Okay, so you have a particular value for the derivative at this x0, right? Right. So what is the derivative at this point? Is it increasing or decreasing? What is your idea? Will it increase or decrease? At this point, the derivative will be more or less. Please respond on the chat, please. We have discussed this concept yesterday. Comparing to x0, do we have a lesser derivative at this point or not? Please do respond. What will be the nature of derivative at this point? Will it be less or more?
So it will be a
Sir,
minimal one.
it's less.
At this
It will be
point,
less.
see,
Uh,
on
Towards the
moving
corners, it will be
this direction, will the slope increase or decrease?
decreases.
See, at this point, the slope is like this. At this point, the slope is like this, which is more, which is having more angle. Did you get my question? Like, for all, I'm asking you one more time. Okay, I will. Suppose you are having a function like this. Okay, you will be having one point here, x0, and another point here, x1. At which point the derivative will be high? You can see, you can consider the tangent over here. See, this angle is less than this, right? And derivative is equivalent to tan theta. So which one is more? At x0 or at x1? At x1 will be more, right? And what is the definition of gradient descent? What is the definition of gradient descent? The gradient should be decreasing. So if this is the direction where the derivative increase, we have to move in the opposite direction of it, right? So on the next updation, what we have to do? We need to move towards the next towards the uh, smaller direction or bigger direction? So what we have to do? Starting from this point, x0, we have to move in the negative direction of gradient. Okay, right? This is how gradient descent will reach the optimum point. Okay, gradient descent will reach the optimum point. Okay, so this is exactly what happening here. So, and what is the updation here? What is the updated value here? It is nothing but xi plus 1 is equal to xi minus, that is the negative direction of gradient of this function, right? But for some time, what will happen is, see, on jumping higher values, there may be a chance of getting skipped with the optimum point. Okay, so why this is happening? Because this gradient will be very big. Okay, this gradient will be very big. So we only need to consider a fraction of this gradient. So for that, we are multiplying the gradient with a constant value, which is less than 1. Then only we are subtracting that from xi. And this alpha is actually called as, or this alpha is actually called as what? Learning rate. What is that? That is what we are calling as learning rate. Okay, this is called as learning rate. So gradient descent is nothing but simply if you have a curve, if you have a function as a surface, it will start from a random point, and by moving towards the negative direction of gradient, you can reach to the optimum point, right? That is what we are calling as gradient descent. Okay, so with this gradient descent, we will define a new algorithm called back propagation learning algorithm. What is that? Back propagation learning algorithm. So how the back propagation learning algorithm works, you can see here, right? See, first you will give an input. At the output point, you will get a predicted value, and that predicted value will be compared with the actual output. Then you will get an error. Okay, you will get an error. So I will be depicting that concept on a neural network, simple neural network here. See, suppose you are having a neural network like this. Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 weights are there, right? W1, W2, W3, W4, W5, W6, W7, and W8. Okay, right? Now, I'm giving the input 1, 2, 1, and I'm obtaining the output 13 here, and the expected output is 70. So there is a difference, 13 minus 17 whole square. Maybe for 16 is the error. And the question is, who is responsible for this error? Who is responsible for this error? Can you think of it? Who is responsible for this error? The incorrect values of W1, W2, W3, etc. up to W8 is responsible for this error, right? So I can say the error occurred in a neural network E is a function of the corresponding weights in the network W3, W4, W5, W6, W7, and W8. So the total error happened on this neural network is due to W1, W2, etc. up to W8. Then how can you contribute? How can you find the contribution of each weight towards the error? That is a key. How can you find the contribution of each weight towards the error? How can you do that? Think of it. We have explained that yesterday. If a function is depending on multiple variables, independent variables, the change happening on that function is actually impacted by all these independent variables. To find out the contribution of each independent variable towards this function, what we can use? Someone is actually trying to say it. Tell it, please. What mathematical concept I can use for that? The contribution of W1 towards the error E. We have calculated the error. Now I want to calculate, I want to know what is the contribution of each weight towards that error. Yes, exactly, Selina ma'am. Exactly the partial derivative. So you can find the contribution of W1 towards that error as dou E by dou W1. Okay, dou E by dou W1. And now you can optimize W1 with the help of gradient descent. How? W1 is equal to W1 minus alpha into dou E by dou W1. Okay, dou E by dou W1. Okay, right? So generally for all weights, W1, W2, W3, etc. up to Wn is updated as W1, W2, W3, etc. up to Wn minus alpha into dou E by dou W1, dou E by dou W2, etc. up to dou E by dou Wn. And this is what is described with gradient descent. The weight vector W is updated as W minus alpha into gradient of E with respect to W, right? And this is what we are calling as gradient descent. Okay, and this gradient descent is applied on back propagation to update the weights. And finally, this updations will happen and happen and happen for all the inputs. You will arrive at a proper set of weights which will give the minimum error. Okay, so hope it is clear for you, right? So this is a simple mathematical explanation of how this is all happening. So I want to convey one more term here that is a very important term. You may be hearing to that. That is called as vanishing gradient problem. Vanishing gradient problem. Okay. So how this vanishing gradient problem can be explained? See, here we have the input, the weight 1, the hidden layer 1, weight 2, the hidden layer 2, and the output. Okay. And the error is calculated from here, right? So here I can say error is calculated by from Y. Error is calculated from Y, right? And how this Y is obtained? O1 and O2. How this Y is obtained? Y is actually depending on O1 and W1. And this O1 is depending on what? X and W2, right? X and W2. So how can you calculate this? Oh, y O2, I can write it as well. How can I calculate the partial derivative of E, dou E by dou W1? It is dou E by dou O2 into dou O2 by dou W1, right? Because W is not directly connected to E. W1 is connected to O2, O2 is connected to E. So dou E by dou W1 is dou E by dou O2 into dou O2 by dou W1. Again, dou E by dou W2 can be calculated as dou E by dou O2 into dou O2 by dou O1 into dou O1 by dou W2, right? See, so for finding the weight which is very nearer to the output node, we need to multiply two derivatives, right? For finding the partial derivative of W2 with respect to, sorry, E with respect to W2, we need to multiply three derivatives, right? So what is the intuition we can have? As we are moving away from the output node, to find the partial derivative, we have to multiply more number of intermediate derivatives, right? So suppose there is a big neural network with 10 or 15 or 20 layers. Okay, what will happen to find the, say this is some dou E by dou W1. To find this dou E by dou W1, we have to multiply a lot of derivatives, right? Assume all these derivatives are 0.1. what will happen? 0.1 into 0.1 into 0.1 into 0.1. What will happen? This derivative value will be approximately equal to what? 0, right? That is, the gradient will become dou E by dou Wi become 0. So what will happen in the equation? Wi equal to Wi minus alpha into dou E by dou W1, right? So if this become W1, what will happen? Wi plus 1 remains what? Wi. That is, no updation will happen on that particular weight. So the problem will not get tackled properly, right? This problem is actually called as vanishing gradient problem. Okay, as the number of hidden layers increases, at the beginning layers, the gradient calculation become approximated to 0. Due to this, this gradient descent won't work as the weight updations are not happening on the initial layers. Okay, so this concept is actually called as what? This is what we are calling as vanishing gradient problem. Okay, so as I said, we have used the gradient descent for this, right? So similar to gradient descent, there are a lot of other kind of optimization techniques exist. The one is stochastic gradient descent, the mini batch gradient descent with stochastic gradient descent with momentum, and other thing like ADA delta, RMS drop, ADAM. These are the different kind of choices we have for optimizers. We cannot say this particular optimizer is good for a particular problem. It's always a need to do a trial and error for finding the optimal optimizer for a particular problem. Okay, so keep in mind there are a lot of optimizers. All are actually doing the same thing. All are actually traversing through the error surface. Some will move faster way for some problem. The others will move in another way. Okay, that is the only difference. And the choice of activation function, because in the previous example of perceptron, we had taken the unit step function as a grade, as a activation function, right? As an activation function, right? But in some cases, we need to go for other activation functions like sigmoid. What is the purpose of that? See, in the case of a binary classification, say it is correct. And from the output node, we have to either fire as 0 or 1, right? But for multi-class classification, what will happen? How can I actually output if there are 4 classes? 0, 1, 2, and 3. Is it possible to output like this? Is it possible to output like this? No. So what we usually do is, instead of keeping one neuron at the other end, we will keep 4 neurons representing 4 classes. Okay. So the output from each of this neuron at the output layer should be a probability between 0 to 1. Probability between 0 to 1 that represents the membership of that particular, or the chance of being that input towards this output class 1, 2, 3, and 4. So the output reaching on this output node will get squashed into a value between 0 to 1, right? For that purpose, we are using the sigmoid activation function. Okay, sigmoid activation function will squash every input into an interval of 0 to 1. Okay, that is what we are calling as sigmoid activation function. Suppose if the interval you have taken is not 0 to 1, it is -1 to 1, you can use TANH activation function. And there is something called ReLU activation function. This ReLU activation function is actually for handling the non-linearity, because this function is not particularly differentiable. Okay, so it will tackle the vanishing gradient problem, and it prevents the vanishing gradient vanishing problem. So if you are considering a multi-layer perceptron, we will keep this ReLU activation function as the activation functions in the intermediate layers. Only at the output layer, we will keep the sigmoid, softmax, or say tanh kind of functions. Okay, so that part is there for mapping your output into required form. And finally, for calculating the error between the actual output as well as the predicted output, we need some mechanisms. According to the different problems, we can go for different error or loss functions. Okay, for regression problem, we can go for this mean squared error, mean absolute error, root mean square kind of stuff. And for classification, we usually go for this binary cross entropy and categorical cross entropy. For binary classification, we use binary cross entropy. For multi-class problems, we will use categorical cross entropy. Okay. And finally, concluding with the introduction to deep neural networks, see, you can observe both are multi-layer perceptrons, right? But what is the difference you can observe? It is having more number of hidden layers, right? So a multi-layer perceptron with more number of hidden layers can be viewed as a deep neural network. Particularly, we say if the number of hidden layers are more than 3, we can actually call it as a deep neural network. And one other particular property of a deep neural network is that, see, in machine learning, if you have an input, you have to do the feature extraction part, and then with that features only the neural networks or whatever algorithms are working, right? But in the case of deep neural network, the network itself is capable of identifying the relevant features for classifying or for doing the regression or whatever task it is. The network itself is capable of extracting the features in a proper way. So that's all. These are the takeaways we have discussed: the mathematical foundations, neural network, perceptron, multi-layer perceptron, gradient descent, backpropagation, optimizers, activation functions, loss functions, and an introduction to deep neural networks. So thank you for patiently listening for this much time. Hope the session was fruitful to you. And if you have any questions, you can ask. Yesterday, I didn't get any questions from any of you. Maybe I was thinking that it was because of the mathematical overloaded. But now it is a neural network. If you have any doubts on this, you can ask. The floor is open to you. And be connected with me. This is my phone number and email address. If you want to get any kind of help on this part or any kind of clarifications, you can actually connect with me. Okay. Thank you.
Thank you, sir, for the highly informative session. Do we have any questions from the participants? Since there are no further questions, we will conclude the session here. Before we conclude this session, I request all participants to kindly switch on your cameras for a quick group photograph. Thank you very much, sir, for your insightful and engaging talk. Your perspectives have truly enriched our understanding of neural networks. Now, before we conclude, I kindly request at least 3 participants to share your quick feedback on today's sessions. Your reflections will add more value to this FDP.
Good evening, ma'am. This is Arun giving my feedback here. Both the sessions were very informative and was very engaging, and it was a very great experience for me. And the sessions were insightful, especially Mr. Mohammad Afzal has given a very good approach and the various approaches for ML algorithms, and the sessions were very insightful. And he's much focusing on the practical session and the industrial session. That was very nice here. And the session 6 about the unraveling neural networks, Dr. Shailesh Sivan sir. And a special thank to you, sir, because you gave a very good delivery of understanding, the better understanding. And being a mathematics one, the way you conveyed and delivered things was very nice. And it was a very great experience. Like the way even I understood was very good. The way you delivered things was slow, steady, and very approachable. And it was very nice. And we have learned a lot here. And special thanks to the organizing team for providing such a very good platform for the faculty development and upskilling their knowledge. Very thankful, ma'am. Thank you, ma'am.
We have also shared the feedback link in chat. Kindly make sure to fill it out as it is essential for certification and for improving future programs. With this, we officially close day 3 of the ATAL FDP. Thank you once again, and we look forward to seeing you tomorrow. Wishing you a pleasant evening.
Thank you.